All right, in Chapter 4, Section 3, we're going to be looking at metathesis reactions. And the very first type of metathesis reaction that we want to look at is acid-base reactions. To do that, we need to get a little bit of background on acids and bases. And so here I've got a Venn diagram of the acid universe. Inside this big circle, we've got everything that we reasonably could call an acid. Inside that circle, there is a much smaller subset of these things that we could call acids that are traditionally what we think of as acids, and they are considered Arrhenius acids. So Arrhenius acids are things that when we put them into water, they increase the concentration of the hydrogen ion, typically by giving up H plus from the molecule. So those are called Arrhenius acids. Now, there is a broader category of acids that we will refer to that are called Bronsted-Lowry acids. Bronsted-Lowry acids are things we first of all get rid of the need for water. So we don't have to have water in the definition for Bronsted-Lowry acids, and then we also focus just on the H plus, and so we call it an H plus donor. So Bronsted-Lowry acids are H plus donors. Now, there is a broader category of acids that gets rid of the need to have hydrogen involved at all, and for those, we call them Lewis acids. Lewis acids are what we call electron pair acceptors. Now, we're not ready to talk about Lewis acids in any great detail because we haven't done the structures. We haven't looked at like electron pairs and things like that in molecular compounds. So again, we're not ready to talk about Lewis acids. We will talk about that in the second half of the semester. So in this chapter, we're going to focus mostly on Arrhenius acids. So we'll focus mostly on Arrhenius acids. We'll just ever so briefly talk about the Bronsted-Lowry, but we're going to focus almost entirely on Arrhenius acids. So when we talk about acids, not all acids are created equal. Some are considered strong acids. Strong acids are acids that when we put them into water, they dissociate 100%. A common example of a strong acid is hydrochloric acid. When we put it into water, it will dissociate 100%. And by 100%, I mean essentially 100%. For HCl, it's like 99.999% or something like that. It's almost 100%. But even if it were just 99%, we would probably say, that's close enough. We'll call it 100%. So strong acids dissociate essentially 100%. Weak acids are somewhat less than 100%. And an example of a weak acid, and I picked one that's in the same group, and that is hydrofluoric acid. Hydrofluoric acid, even though it's in the same column as HCl, so chlorine and fluorine are both in group 7, we'll find that when we put it into water at a typical concentration of 0.1 to 1 molar, that it only dissociates about 5%. So only 5% of the molecules will dissociate. And so it's considered a weak acid. Now, one thing that I want to emphasize here is just because something is a strong acid doesn't mean that it's necessarily super dangerous in every application. Sure, yeah, HCl, if you were to get HCl in your eye, that would be really bad because acids don't do well. They are damaging to your corneas. So having a strong acid in your eye is quite dangerous. However, HCl is actually quite common in the body. It is the acid that is in stomach acid. Often it's called muriatic acid, but it is the acid that makes your stomach acidic. So I mean, you've got a really strong acid right there in your stomach. This is why if you happen to throw up and lose your stomach, that it is really, really uncomfortable and painful when that stuff comes up. So it's because of that acid that is present. Now, if you were to take hydrochloric acid and accidentally spill some on your hand, it would be uncomfortable and you should rinse it off right away. However, it probably is not going to cause any permanent scarring or damage if you rinse it off fairly quickly, particularly if it's not at a very high concentration. That said, disclaimer here, don't pour it on your skin. But if you accidentally get a little bit on your skin, rinse it off and you should be fine. Hydrofluoric acid, on the other hand, even though it only dissociates about 5%, the procedure for getting it on your skin is 1, rinse it off, just like you do with the hydrochloric acid, but 2, you put the antidote on, 3, you cover it with latex, 4, you rush yourself to the hospital or have somebody, take you to the hospital. And that's because it is quite dangerous. It does all kinds of nasty things to your body, and it all has to do with that fluoride ion that is present in hydrofluoric acid. So it is much, much more dangerous. I used to work with hydrofluoric acid on occasion when I was in graduate school, and the procedures that I used for working with hydrofluoric acid was first I would put gloves on, and then a long lab coat that covered my arms completely. Then I would put goggles onto my face. I would put a face mask that covered my goggles. Then I would put thick gloves on over my regular gloves. So I would double glove, and that would give me an extra layer of protection in case there was some sort of hole in either of the gloves. Then I would get that extra layer of protection. And then I would work with it in the hood with the sash pulled down so that the sash was in between me and the chemical as much as possible, so that I would be unlikely to get it on my face or anything. In other words, working with HF is a very risky business, and definitely something that you should be trained to do before working with it. So don't ever attempt to work with HF unless you are in a properly equipped facility, and you would definitely want to have the antidote ready to go, and be trained in what to do in case you were to get exposed to the HF. We do not keep any hydrofluoric acid in our labs on the North Lake campus, and that is simply because it is just too dangerous to work with in any sort of normal conditions. So, all right, little public service announcement: don't mess with hydrofluoric acid. It's bad stuff. In a similar fashion, if you have a fluoride, if you have like sodium fluoride and you treat it with a strong acid, you're going to get HF. So stay away from fluorides in any significant concentration. Now, some of you may be thinking, well, what about sodium fluoride or tin fluoride that is in our toothpaste? Well, there it's 1, in a very low concentration, and 2, it has a beneficial effect. For your teeth, and 3, you're supposed to spit out your toothpaste, right? So, small amount onto your teeth, and then you spit it out, and that's fine. You don't want to swallow the toothpaste. That's a bad idea. Okay. So now that I've given you that public service announcement about strong acid versus weak acid, I want to show you a list of 7 strong acids. I want you to memorize this list. All right, we've got hydrochloric acid, hydrobromic acid, and hydroiodic acid. If you look on the periodic table, you will see that these are the acids. And here, I'm going to get the periodic table. Here you go. So these are all in group 7. So hydrochloric, hydrobromic, hydroiodic. All right, so those are all in group 7 on the periodic table. HF is the only one in that group that is not acidic. If we go down further to HAT, the astatine may be a strong acid, but again, it's radioactive, and so we're not going to mess with it. Next, we have nitric acid, which is a strong acid, chloric acid, perchloric acid, and sulfuric acid. I want you to memorize these. There are only 7 here that you have to memorize, and it's pretty easy to do this. So those three that are in group 7, and then nitric, chloric, perchloric, and sulfuric. The reason I want you to memorize these is, like I said, there's only 7. And when it comes to weak acids, there are many thousands of them, and it's impossible to memorize all of those. So memorize your 7 strong acids and you'll be good. Oh, spoiler alert, if you go on to take organic chemistry, I'm going to tell you about a couple others, but they are fairly uncommon, and they are related to sulfuric acid. So they're kind of related to that. But memorize these, you'll be good. All right. Just like for acids, we also have bases that we can look at. And so everything that fits in this big oval is considered a base, but we have a much smaller subset of those things that we call Arrhenius bases. These are typically metal hydroxides, but these are things that when we put them into water, they increase the concentration of hydroxide ion in water. And so here you'll see that the focus of this definition for bases is on hydroxide in water. There's a broader definition that we like to use, and we use this quite a bit in organic chemistry, and that is the Bronsted-Lowry base definition. And if you recall, the Bronsted-Lowry acid was an H+ donor. Well, a Bronsted-Lowry base is an H+ acceptor. All right, so it is an H+ acceptor. All right, our even broader definition, and again, we're not quite ready to talk about this in great detail. I just mention it so that you're aware of it and that you'll see it later in General Chemistry 2, and that is Lewis bases. Lewis acids were electron pair acceptors. Lewis bases are electron pair donors. So, as I mentioned, we're going to focus mostly on Arrhenius acids because those are the ones that are relevant to what we are doing right now. So we've got what we refer to as the strong Arrhenius bases. These are all metal hydroxides that when we put them into water, they will dissociate 100%. They include lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. All right, you'll notice all of those are in group 1. And then the bottom 3 that are in group 2, calcium hydroxide, strontium hydroxide, and barium hydroxide. Just like with your strong acids, I want you to memorize these. So I want you to memorize these. All right. So, and just for reference, go back over to our periodic table. So lithium, sodium, potassium, rubidium, and cesium hydroxide, and then also calcium, strontium, and barium hydroxide. So those are all considered strong bases. All right. Here we've got our weak Arrhenius bases. These are metal hydroxides that when we put them into water, they're just not very soluble in water. And since they're not soluble enough in water, we generally don't consider them strong bases. These include things like magnesium hydroxide. You'll see that it says solid over here on the left, and that is if you take a chunk of magnesium hydroxide and you drop it into water, you won't see much happen. A little bit will dissolve, but most of it won't. You will get a little bit of magnesium and hydroxide, and to the extent that that happens, you increase the concentration of hydroxide in your solution. However, in 1 liter of water, only about 96 milligrams of magnesium hydroxide will dissolve in pure water, and that's at 25 degrees Celsius. So we will talk about these kinds of bases, how soluble they are, a lot more in the second semester. All right. One other thing that I want to point out before I move away from this is that all of the other metals, all right, so if we look here, all of these beige colored things are metals. So all of these are considered metals. Of of those, most of them form hydroxides, and only these 8 are really considered strong bases. The rest, all of these over here, including like lead and bismuth, when they form hydroxides, they are considered weak, and that's just because they're insoluble. Now, I will point out that francium hydroxide and radium hydroxide are probably soluble in water, and they're probably strong bases, but they're also really, really radioactive, so we're going to kind of put them in a different category. We don't want to do any experiments with those. They might kill us, right? That would be bad. All right, so we'll go back here to our presentation. All right, we also have nitrogen-containing bases, and these nitrogen-containing bases, like ammonia, when we put them into water, they only dissociate a little bit. The amount that they dissociate depends on how strong of a base they are, but they only dissociate a little bit. Ammonia, for example, when we put it into water, about 1% of the ammonia molecules will dissociate to give us ammonium ions and hydroxide ions. So 99% of them are going to stay in the form of ammonia. Now, this is an equilibrium process. You'll see the double arrow here. It is an equilibrium process, so we are going to see we're going to all the molecules eventually will be dissociated, but not at the same time. So, but only 1% at a given time are going to be dissociated. So we consider those weak electrolytes and are not going to be strong electrolytes. All right. So next thing we want to look at, we're going to look at this actually the dissociation of ammonia a little bit more closely, just to give you a taste of the Bronsted-Lowry acid-base definition. So here you'll see that water donates H+ to ammonia. And when it donates the H+ to ammonia, the water becomes hydroxide and the ammonia becomes ammonium. Since water is donating H+, it is considered a Bronsted-Lowry acid. And since ammonia is accepting H+, it is considered a Bronsted-Lowry base. All right. We're going to talk a lot more about Bronsted-Lowry acid-base definitions in the second semester, but I do like to give you that, plant that idea in your head so that later it doesn't seem so strange. All right. The main focus that we want to look at here are metathesis reactions. And the metathesis reaction that we want to look at is a neutralization reaction. A neutralization reaction between an acid and a base. So when you have a Bronsted-Lowry acid and it reacts with a metal hydroxide, so a Bronsted-Lowry acid, it's also an Arrhenius acid, reacts with a metal hydroxide, it will produce water and an ionic compound. And the generic term that we give for an ionic compound is salt. If you're talking salt in just regular English, we're talking about sodium chloride, which is the example that is given here. However, if we're talking salt in the chemistry sense, a salt in chemistry is just an ionic compound. So here on the left, you'll see that we've got our strong acid and our strong base, so HCl and sodium hydroxide. They react to give us water and sodium chloride. So react to give us water and sodium chloride. This is a metathesis reaction. So the hydrogen ends up with hydroxide to give us water. The sodium ends up with the chloride to give us sodium chloride. The driving force for this metathesis reaction is the formation of the non-electrolyte water. So if you recall, there were 3 driving forces. There was the formation of a precipitate, which we spent the whole last section talking about. There's the formation of a non-weak or non-electrolyte, which is this, and the formation of a gas, which we have coming up here in just a few minutes. All right, and there is our non-electrolyte water. So we want to be able to take these, and just like with our precipitation reactions, we want to be able to write our molecular, complete ionic, and net ionic equation. So here is our molecular equation. Always have to get that correct and balanced before you go on to the molecular, or the complete and the net ionic equation. To get to the complete ionic equation, we need to dissociate anything that is a strong electrolyte. Things that are included as strong electrolytes are strong acids, strong bases, and soluble ionic compounds. Well, this particular equation has all three. HCl is a strong acid, sodium hydroxide is a strong base, and sodium chloride is a soluble ionic compound. So those three things we are going to dissociate. The only thing we don't dissociate is water, because it is a non-electrolyte. So the HCl will dissociate to give us hydrogen ion and chloride ion. Sodium hydroxide will dissociate to give us sodium ion and hydroxide ion. Water we're going to leave together. And then sodium chloride will dissociate to give us the sodium ion and the chloride ion. Now that we've got that, we want to, that's our complete ionic equation. We want to get to our net ionic equation. Our net ionic equation, we can get to it by crossing out our spectators. If we look here, our spectators are going to include chloride ion and sodium ion, and those cancel out. And so there is our net ionic equation. Interesting factoid here: if you have a strong Arrhenius acid with a strong Arrhenius base, then this will be your net ionic equation. So if you have a strong Arrhenius acid and a strong Arrhenius base, this will be your net ionic equation, which that's kind of cool. All right, so the next thing we want to do is, what if we have an insoluble base? So what if we have something like magnesium hydroxide? The net ionic equation will look a little bit different, but the procedure is very, very similar. So here is the reaction between hydrochloric acid and magnesium hydroxide. So you'll notice that because there are two hydroxides with the magnesium, that means we're going to need two equivalents of acid in order to react with it. And when we do that, we're going to get two water molecules, and we will get magnesium chloride. Now, when you're writing these, if you just look at how many hydroxides there are, that's how many water molecules you're going to end up with. So we need to dissociate all the strong electrolytes here. Well, HCl is a strong electrolyte. Magnesium hydroxide isn't, because it's a solid. Water is not a strong electrolyte. It's a non-electrolyte. And magnesium chloride is a strong electrolyte. So we're going to dissociate the HCl and the magnesium chloride. We do need to pay attention to that coefficient, and we also need to pay attention to this 2 here. So when we dissociate the HCl, we'll get 2 hydrogen ions and 2 chloride ions. Magnesium hydroxide will stay the same. Water will also stay the same, but then we'll get a magnesium ion and 2 chloride ions. To get our net ionic equation, we're going to cancel out our spectators here, and our spectators are chloride, and that will give us that as a net ionic equation. All right, well, we're going to go to number 39 on the in-class assignment. All right, so number 39. Yeah, so number 39 here, we've got 2 of these, and we want to balance them. All right, so we want to write out the molecular equation, the complete ionic equation, and the net ionic equation. So just like with before, it's helpful if you write down what the ions that you're dealing with are. So we know we have H plus and bromide, and here we've got the calcium 2 plus and hydroxide. Now, you don't necessarily have to do that, but it is a little bit helpful. We know this is an acid-base reaction, so hydrogen is going to end up with hydroxide to give us water. So we'll have H2O liquid there. And then the other compound is calcium bromide. Calcium is a 2+ charge. Bromide is -1. So it will be CaBr2. And that is a soluble ionic compound. So I will put AQ there. All right. And that would give us what we want. Now, one thing real quick, this is not a balanced equation. We need to balance this before we can move on. So let's start with bromine because bromine is our biggest element. Bromine, we have 2 here and 1 there. So I'm going to put a 1 to lock those 2 in place, and then we'll put a 2 out front in front of HBr. Next, let's look at calcium. We have 1 calcium here, so we're going to put 1 in front of calcium hydroxide there. All right. Next, let's look at oxygen. We've got 2 oxygens represented here. 1 times 2 times 1, that's 2. To get 2 oxygens out of this, we'll put a 2 in front of the H2O. Now we want to dissociate anything that is a strong electrolyte. Well, this is a strong electrolyte because it's a strong acid. This is a strong electrolyte because it's a strong base. And this is a strong electrolyte because it is a soluble ionic compound. Water isn't, so we're not going to dissociate it. We do need to pay attention to the coefficients and to subscripts when we are dissociating things. So we will put 2H plus AQ plus 2 bromide AQ plus calcium 2 plus AQ plus 2 hydroxides AQ. On the right side of the equation, we're going to leave the water like it is. So 2H2O, liquid. And then we'll have 1 calcium ion, so 2 plus AQ, and 2 bromide ions, AQ. All right. Now that we've done that, we want to cancel out things that are spectators. Here our bromide ions are spectators, our calcium ions are spectators, and what is left over is 2H plus AQ plus 2 hydroxide AQ gives us 2 H2O liquid. Since all of the coefficients there are 2, we could conceivably divide them all by 1, or divide them by 2, and simply get H plus hydroxide gives us H2O. And I think I mentioned this earlier, that anytime you have a strong Arrhenius acid and a strong Arrhenius base, then that would be your net ionic equation. So H plus hydroxide gives us water. All right, and that is the end of that particular problem. Let's look at part B. And here we've got copper hydroxide, and you'll see that that's copper 2 hydroxide because of the 2 there. So I'm going to go ahead and put that here. So Cu2 plus hydroxide is -1. HCl dissociates to give us H plus and chloride. All right, well, clearly we're going to form water. So I typically will write the water first. So I'm going to put H2O liquid right there. And then the other compound is going to be copper chloride. Since it's copper 2, we will end up with CuCl2, AQ. All right, this isn't quite balanced yet. So what we want to do is we want to balance it. Copper is our biggest element, so we'll lock those coppers in place. We'll put 1 and 1, so that's balanced. Chloride is next. We've got 2 chlorides there. We only have 1 here, so we'll put a 2 out front there. And now for oxygen, we've got 2 hydroxide, 1 times 2 times 1. That gives us 2 oxygens. And so we'll put a 2 in front of the water molecule. And I think I mentioned this a bit ago, but however many hydroxides you have, that's how many water molecules you are going to have. That's a convenient little trick to do when you're doing this kind of problem. All right, well now let's do our complete ionic equation. We're going to dissociate anything that is a strong electrolyte. Well, this isn't because it's a solid. This is, because it's a strong acid, that's water, and that's not a strong electrolyte. And then copper chloride is a soluble ionic compound, so yes, it is indeed a strong electrolyte. So we'll leave the copper hydroxide together, so CuOH2 solid plus 2H plus AQ plus 2 chloride AQ gives us 2 H2O liquid plus copper 2 plus AQ plus 2 chloride AQ. All right, now that we've done that, we'll look for spectators. You'll notice that on this one, we only have one spectator. That's normal when we have these insoluble bases. So we only have one, and that's the chloride. And what we're going to be left with is CuOH2 solid plus 2H plus AQ. On the product side, we'll get 2 H2O liquid plus copper 2 plus AQ. Okay, well that is our last example of that one, and so we'll go back over to our presentation, and we're going to look at another type of metathesis reaction that are called gas-forming reactions. This is the third type that I was mentioning a little bit earlier. So if you were to take calcium carbonate and HCl, it would do a metathesis reaction. So the hydrogen would end up going with the carbonate, and the chloride would end up going with the calcium, and we would get calcium chloride, and you would think that we would get H2CO3, which is carbonic acid. Well, like I said, you do actually get that, but it doesn't stay like this. Instead, what happens is that it actually goes a step further instantly to give you carbon dioxide and water. And if you add all those up, that adds up to the same as the carbonic acid. Just so happens that whenever you take carbonic acid, or whenever you take carbon dioxide and water and you dissolve the carbon dioxide in water, you get carbonic acid. So anytime you are drinking a carbonated beverage, part of what you're drinking is carbonic acid, which is kind of cool to think about. Over here, we've got the calcium carbonate and the HCl. The key to this is anytime you take a carbonate and treat it with acid, this is going to happen. You'll end up with carbon dioxide and water instead of just carbonic acid. So you have to be able to recognize this when you've got carbonates. All right. There are some similar gas-forming reactions that I want you to be aware of. It happens with not just carbonates, but bicarbonates, sulfites, and bisulfites. So here is another carbonate, sodium carbonate plus HCl, of course, gives us the sodium chloride, and then we get carbon dioxide and water. So if you've got carbonate, you'll get CO2 and water. In a similar fashion, here we've got potassium bicarbonate, and potassium bicarbonate with this acid will end up giving us carbon dioxide and water. All right. Here we've got sulfite, and so strontium sulfite, if you put it into a strong acid solution like this nitric acid, you will get strontium nitrate, but you will also get sulfur dioxide and water. So instead of getting carbon dioxide, you get sulfur dioxide. Now, I'm going to mention this. If you decide to try this at home, which I'm probably going to say don't do this, because that sulfite, when you treat it with the acid and you get that sulfur dioxide has a very strong pungent odor. I mentioned this before, but whenever you strike a match and that burning sulfur smell, well, that burning sulfur smell you smell is sulfur dioxide. And in small concentrations, it's like, oh, that's a burning match, right? Or that's burning sulfur. In high concentrations, it can be quite unpleasant. So just mention that. All right. In a similar fashion, if you take a bisulfite and you treat it with acid, you will get sodium chloride, uh, um, uh, and you'll get sulfur dioxide and water. So if you've got carbonate or bicarbonate, you'll get carbon dioxide. If you've got sulfite or bisulfite, you'll get sulfur dioxide. One other thing I want to mention about it is with the carbonate and sulfites, it takes 2 equivalents of the acid to neutralize that so that you can get the carbon dioxide and water. With the bicarbonate or with the bicarbonate and the bisulfite, it only takes 1 equivalent, and that's because these already have 1 hydrogen associated with them. So that's just a stoichiometry thing to be aware of. All right, and of course, you need to be able to do your net ionic equations for these. So for carbonates, this is one that we saw earlier. We dissociate anything that is a strong electrolyte. So this is not because it's not soluble. This is because it's a strong acid. This is because it's a soluble ionic compound. This is not because it's carbon dioxide. It came out of the water, so it is not a strong electrolyte. And of course, water itself is not a strong electrolyte. So we'll dissociate the HCl, pay attention to the coefficients. So we ended up with 2 hydrogen ions and 2 chloride ions. With this one, pay attention to that 2. We'll end up with 1 calcium and 2 chlorides. Carbon dioxide and water, we leave it together. To get from, this is our complete ionic equation, to get from the complete ionic equation to the net ionic equation, we need to cross out our spectators. Our spectators here are chloride, and that's it. You'll notice nothing else will cancel out. And so that gives us our net ionic equation. All right, I've got one more here, one more gas forming reaction, and this one is really interesting because it is very, odoriferous. It's stinky. All right, so metal sulfides, when you put them in there, and because it's so stinky, you should carry them out in a hood. So this is not something you should do at home. But here we've got sodium sulfide plus an acid, sulfuric acid in this case, and we'll get the metathesis, so sodium sulfate and H2S. Right up front, that looks like just a straightforward metathesis reaction, and it is. The only thing that's really different is that H2S gas is, or H2S here is a gas, and that gas is the smell of rotten eggs. And so whenever you smell rotten eggs, you're smelling H2S. And if you were to do this at a high concentration, you would get a lot of that rotten egg smell. So this is something that should be carried out in a hood and at very small quantities. In large quantities, it would be very unpleasant. Now, one quick note. If you've ever been to a hot sulfur spring, so for example, there's actually a place in Arkansas called Sulphur Springs. There are many places up in the mountains of Colorado that have some sulfur springs. One I like to go to in the summer is called Pagosa Springs, and it has a sulfur spring. Really, what happens is hot, somewhat acidic water rushes up from deep in the earth through the crust, and as it's rushing and it's a little bit acidic, as it rushes up, it runs into naturally occurring metal sulfides. Those metal sulfides. Some of the sulfide will get picked up by the slightly acidic water, and you will get H2S gas that comes out with that water. Once it reaches ground level, the hydrogen sulfide comes out of solution, and you get a distinctive rotten egg smell. Is it safe to be around? Well, if you can stand it, it's probably safe to be around. If it's so concentrated that you just can't stand it, you probably shouldn't stick around. So, all right. So just a little interesting factoid there. Let's look at number 40 on the in-class assignment. All right. And just like with before, I'm going to write out the ions just right below it. So we have H plus bromide, and then sodium ion, and then HSO3 minus. That's the bisulfite ion. Well, the sodium and the bromide are going to make an ionic compound, and the hydrogen and the bisulfite ion are going to make sulfurous acid, which instantly decomposes to give us SO2 and H2O. So our products are going to look like this. Our ionic compound is going to be the sodium bromide, so NaBr, and then we'll get sulfur dioxide and H2O. All right. When we go through and attempt to balance this, we will see that this is already balanced. So I'll just show you. We've got two hydrogens here, two hydrogens there for bromine, one bromine. Here we've got one sodium. We've got one sulfur, and then three oxygens and 3 oxygens there. So all of these have a coefficient of 1. And I just point that out because we usually balance these before we move on. So next, we want to determine what are strong electrolytes. Well, it's a strong acid. It's a soluble ionic compound. I forgot to put the AQ there. So AQ, that's a soluble ionic compound. This is a gas, so it isn't, and that is water, so it isn't. So we're going to dissociate all these 3 strong electrolytes. So we will get H plus Br minus plus sodium ion plus the bisulfite HSO3 minus. All right. On the right side, we will get the sodium ion, AQ, plus the bromide ion, AQ, plus sulfur dioxide gas, plus H2O liquid. Now we want to cancel out any spectators. Our spectators here happen to be bromide and sodium. And what's left over is this, H plus AQ plus HSO3 minus AQ. And that gives us SO2 gas plus H2O liquid. All right, for the next one, our ions here, we want to identify our ions up front, kind of like what we have been doing. So here we've got iron carbonate. Carbonate has a -2 charge. And if you look at the subscripts here, you can figure out that the iron must have a 3+ charge. So we're going to have iron 3 carbonate. So those are the ions there. And then, of course, this is H and Cl minus. All right, since this has a carbonate, hydrogen ends up with carbonate, and that's going to give us carbon dioxide and water. And we want to figure out what the ionic compound is. We've got iron 3 and chloride, so we're going to get FeCl3. All right, so FeCl3. All right, for the carbon dioxide and water, so we'll get CO2 gas plus H2O liquid. So the next thing that we want to do is we want to balance it. This is not a balanced equation. Our biggest element here is iron, so I'm going to start with it. We've got 2 irons there, so I'm going to put a 1 there, and then I'll put a 2 here to give us 2 irons. Next, let's look at chlorine. With chlorine, we've got 2 times 3, so that's 6. We'll put a 6 in front of the HCl. Our next biggest element is carbon. We've got 1 times 3 times 1, so that's 3 carbons. So we'll have 3 carbon dioxides. And in a similar fashion, let's do hydrogen. We've got 6 hydrogens here. And to get 6 hydrogens here, we will need a 3 in front of the water. If you go through and count up the oxygens, you'll see that they are balanced as well. So now let's look, what are the strong electrolytes? Well, this is not a strong electrolyte because it's a solid, so we're going to leave it together. This is because it's a strong acid, so we will dissociate the HCl. This is a soluble ionic compound, so we will dissociate it. Carbon dioxide and water, we won't dissociate those. So now we want to write our complete ionic equation. So we'll put Fe2CO3 3 solid. All right, for HCl, we've got 6H plus AQ and 6 chloride AQ. All right, for FeCl3, that is a strong electrolyte because it's a soluble ionic compound. So we'll get 2 Fe3 plus, and we'll get 6 of those chlorides. So 6 Cl minus AQ. And then 3 CO2. All right. Got a little carried away there with my C. All right, so 3 CO2 gas and 3 H2O liquid. All right, kind of got crammed in there, but we got it all in there. So now we want to cross out our spectators. In this case, our only spectator is going to be the chloride. So only that chloride. So now let's rewrite what's left over. Fe2CO3 3 solid plus 6H plus AQ gives us 2 Fe3 plus AQ plus CO2 gas, 3 CO2 gas, plus 3 H2O liquid. All right. So next, that one is completed. And so next we want to look at this one. Here we've got copper sulfide, and you can figure out pretty quickly because sulfide is -2 that your copper must be 2 plus, sulfide is 2 minus. Your acid here is nitric, so we'll have H plus and NO3 minus. So this one's going to be a straight up metathesis reaction where we will get H2S as our gas. So H2S as our gas. And then for the copper, we'll end up with nitrate. Copper is +2, nitrate is -1. So we're going to get CuNO3 2 AQ. Right, so NO3 2. All right, so now that we've got that, we need to balance this equation. Copper is our biggest one, and I'm going to lock the coppers in place by putting 1 in front of each. Now for sulfur, we've got 1 sulfur here and 1 sulfur there, and so that will give us the one sulfur is balanced. And now let's look at nitrogen. So we've got 2 nitrogens locked in place over here. So 1 times 2 times 1, that's 2. And we'll put a 2 in front of nitric acid there. So now we want to dissociate anything that's a strong electrolyte. This isn't because it is a solid. This is because it's a strong acid. This is not because it's a gas. And this one is because it is a soluble ionic compound. When we dissociate the strong electrolytes, well, we'll leave that one together. So CuS solid plus 2H plus AQ plus, don't forget to distribute that 2 NO3 minus AQ. And then over on the product side, this one we'll leave together. So H2S gas plus copper 2 AQ plus 2 NO3 minus AQ. So 2 NO3 minus AQ. All right, now what we want to do is we want to we want to cancel out any strong electrolytes. And our only electrolyte in this case is going to be the nitrate. And so we'll write what is left over, and that will be our net ionic equation. So copper sulfide solid plus 2H plus AQ. And on the product side, we'll get H2S gas plus copper 2AQ. And that is our net ionic equation. All right. Well, that is going to be the end of this video. In the next video, we're going to be looking at the section with oxidation reduction. So I will switch over here.